have seen how, using the ratios of stable isotopes, we can reconstruct the habitats and the histories, both of individual organisms and of social phenomena such as agriculture. We've also seen how the radioactive clock of carbon-14 allows us to estimate the ages of individuals and of societies and the monuments they create. There's an implicit assumption in our carbon-14 age dating, however, that we have yet to acknowledge, and that is that the abundance of carbon-14 in the atmosphere is constant over time. Since, as I've said previously, carbon-14 is constantly produced from atmospheric nitrogen by the bombardment of cosmic rays from space, we are implicitly assuming in carbon-14 dating that everything about this process is constant, so at the moment of death of every plant or animal, the ratio of carbon-14 to carbon-12 is absolutely known. Now, it turns out this is not the case, and the recognition of this, and the means to correct for this effect, came from the study of another natural clock, the annual growth rings of trees. Now, using tree rings will take us back about 12,000 years, but carbon-14 dating can extend 5 times that far into the past. And so we'll need to recruit other radioactive clocks from ocean sediments, from coral reefs, and even from volcanic lava in order to assure the accuracy of our primary dating technique, carbon-14, over the entire course of human evolution. Leonardo da Vinci, as in so many subjects, was the first to suggest that tree rings might record, quote, the history of past seasons, end quote. But like so many of da Vinci's ideas, this idea lay dormant until 1901. In that year, Andrew Douglas was a young astronomer at Arizona's Lowell Observatory. The Lowell Observatory was a special place. It had been built 10 years earlier by Percival Lowell, the eccentric Boston Brahmin of the Lowell family, who had become convinced that there was an advanced civilization on Mars. He had read the reports by an Italian astronomer named Schiaparelli, who had reported with his new telescope to see canali, that was the Italian word, on Mars. And rather than performing a careful translation, in which the word canali should be translated as channels, Lowell immediately took the transliteration of it as canals. Canals, of course, are built by intelligent beings, and so Lowell became convinced that there was a vast civilization on Mars in the throes of a millennial drought that were building this network of canals from the poles of Mars, which are covered in white stuff. He thought they were ice. It is frozen carbon dioxide, to bring water to the parched equatorial regions. And he spent a large fraction of his money to build a large observatory, one of the world's largest at the time, in Flagstaff, Arizona. The special thing about this observatory, which persists with us today, is not so much that it was large, but that it was isolated in a very dark, isolated, high mountain location. One of the first observatories ever to be so placed. And of course, that's where we continue to place observatories today. In any event, Lowell wasn't about to himself spend night after night in the freezing cold looking for those moments in the transparent atmosphere of the Earth in which one could see these putative canal construction projects, and so he hired a whole series of young astronomers to do this, and Andrew Douglas was one of them. My suspicion is that very few of these young astronomers actually believed in Lowell's fantasy about civilizations on Mars, but it was a good job, and in their spare time, when Mars wasn't up, for example, they could use the telescope for other research. In Douglas's case, his primary interest was in the sun's 11-year cycle of magnetic storms, what we call the sunspot cycle, and whether or not this cycle had an effect on climate. Now, the sunspot cycle is not a very good clock. We say it occurs in a peak every 11 years, which then decays away and rises again, but in fact it's somewhere between 10 and 12 years, and the intensity from one cycle to the next is very different. Lowell knew some of this and hypothesized that the spots would affect the sun's energy output, and as a consequence would have an impact on Earth's climate. Now, it turns out 100 years later, this idea is still controversial, but we'll talk a little bit more about that later. The sunspot cycle, as I say, leads to a rise and fall in the number of dark patches on the surface of the sun. These dark patches are caused by the eruption through the surface of magnetic fields in the sun generated below the surface, which spew out lots of energy in the ultraviolet part of the spectrum and actually raise the sun's total output. With satellites in space above the confusing effects of the Earth's atmosphere, we've now been able to measure that the magnitude of this change from the peak of the 11-year sunspot cycle to the minimum is only about 1 or 0.2% in total solar output. Not enough, naively at least, to affect Earth's climate. But we've also reconstructed the record of sunspot cycles back to the time they were first discovered in 1609 by Galileo using the first telescope. And indeed, we see that at times the sunspot cycle reaches a high intensity, as it has for the last 100 years or so, but at other times it is very, very modest even at its so-called peak. Indeed, in a large part of the 18th century, sunspots were very modest, and in the 17th century, just after Galileo discovered them, they disappeared completely for about 75 years. It was these longer-term cycles, century-length cycles, that Douglas was interested in as to whether or not they could be reflected in the annual growth rings of trees, because these growth rings are in effect a monitor of long-term climate. Each year, a tree adds a layer of new wood from the outside. In years where there's plenty of water, the temperature is warm, the growing season is long, a large amount of wood accumulates and the ring is fat. In years when it's very dry, or it's very cold, or the growing season gets a late start, the ring might be very narrow. So Douglas was simply measuring the thickness of the rings as a proxy for the climate of that year in which the tree was growing. Now, this is the perfect calendar because the outermost ring always represents the past year, and the next ring in is the year before that, and the next ring in is the year before that, and as long as the tree is alive, it is always producing rings. Thus, it is completely straightforward to count the rings in and learn the age of the tree. Douglas accumulated a sequence of ring widths from the oldest living trees he could find. In Arizona at that time, they were the giant ponderosa pine, which lived for many hundreds of years. And then, in the dry climate of Arizona, when these trees died, they were often preserved for a long period of time. And he could extend the sequence back further by looking for matches in the patterns of the rings. Say you had fat, thin, thin, fat, 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 thin, fat, thin, fat, thin, fat, in one tree ring that was alive, such that you could date when those rings were formed, and you had another set of rings from a tree that was dead, whose age you didn't know. If you slide them back and forth and find the place where they match up, where the fat matches up with the fat and the thin matches up with the thin, year after year after year, you know you've got a match, and going further back in the dead tree tells you about times that are even earlier. He ingeniously found another source of very old trees in the ancient beams of the lodge dwellings of the Native Americans of the Southwest. These were beams that could have been cut down hundreds or even 1,000 years earlier, with their characteristic pattern of fat and thin rings, could be overlapped with living trees, extending the record back further. By 1930, he had recorded a continuous record of 1,200 years, where he knew every single year precisely of the width of trees in Arizona. This allowed him, among other things, to both date the time that the Anasazi civilization we discussed earlier collapsed, and to understand its cause. In the tree ring record, it was very clear that between 1125 and 1180 AD, again between 1270 and 1274 AD, and finally between 1276 and 1299 AD, there were extended periods of drought. Now you will recall that the Anasazi were dependent for their massive city at Chaco Canyon on agriculture from fields of corn that were up to 50 miles away. In periods of intense drought, that corn crop would have failed and famine might have ensued. In the first droughts in the 12th century and in the 13th century, evidently the civilization continued to thrive. But by the time the drought from 1276 to 1299 came, the pressure on the civilization must have been too great. This is sociologically interesting. As the society gets larger and larger, and more dependent on remote agriculture, the society becomes more and more fragile. This is the theme of Jared Diamond's recent book, Collapse, wherein civilizations from Easter Island to Greenland to the Anasazi, which he also discusses, civilizations grow until they put too much pressure on the natural resources available, and then often collapse. Rain, it turned out, did return to the Chaco Canyon area plentifully in 1300, but the people never did. Chaco Canyon remains empty to this day. In any event, by the time of his retirement, Douglas had a continuous chronology of tree rings extending back for 1,800 years. And, perhaps more importantly, he had established at the University of Arizona the first tree ring laboratory to carry on his research. In 1956, University of Arizona scientists discovered the bristlecone pines, the oldest living trees on Earth. These scraggly trees only grow to about 10 meters, 30 or 40 feet in height, and they live in the high altitudes of the Great Basin of the West, only in a few locations. The most famous of these is in the White Mountains on the border between California and Nevada. And if you're ever there, I strongly suggest you visit. It's really an eerie place. These very scraggly old trees, they just look old. They look like a children's book illustrator's idea of what an old tree should look like. And yet they're not huge around like the sequoias of California, and they're not very tall, and large fractions of them are dead, and they have just a little bit of green still growing on them. These trees are mostly over 4,000 years old. In 1964, Donald Curry, a young geologist in the Carolinas, had for his summer project the goal of finding the oldest of these trees. Now, of course, one doesn't have to cut down a tree to find out how many rings there are. There's a little thing called a Swedish borer. It's like a little crank you can crank into the tree and then wind it out again and pull out a pencil-sized piece of wood where all of the rings are clearly delineated. And so off went Donald Curry to the White Mountains with his Swedish borer to measure the ages of the oldest trees. He had a permit from the Park Service, which runs this area, to cut down one tree if that became necessary. He scouted around and picked out the oldest tree. Now, parts of this story may be apocryphal. There are many versions of it you can find on the web, but the outcome certainly happened. He ground his Swedish borer into the tree, and when he pulled it out, he was astonished to see that the tree was nearly 5,000 years old. He went to the next tree that he found and ground the borer in, and it got stuck, hopelessly stuck. And so he went to the Park Service representative and said, "Here's my permit to cut down a tree. Come help me cut down this tree because I have to get my borer out." He did, and that tree was over 5,000 years old. Indeed, as far as we know, it was the oldest living thing on Earth, and Donald Curry cut it down. Today, the oldest living bristlecone pine is known as Methuselah. It's 4,809 years old as of 2009, and it is not labeled in the White Mountain Forest for fear that some vandal will do something bad to it. In any event, these are the oldest living trees, but using the technique pioneered by Douglas, one can also look to dead trees and overlap their sequences to extend the record back even further. Trees that fall in bogs, or particularly in the muddy rivers of northern Europe like the Rhine, are beautifully preserved in that mud, just as Ötzi was preserved in his glacier in the Alps. And cross-correlating the ring-width patterns of the living and the dead trees, we have now managed to produce a continuous record extending back nearly 12,000 years. The interaction of carbon-14 dating and tree ring dating has led both to a surprising rewriting of ancient history and to the revelation that the Earth's magnetic field changes over time. The connection between these two disparate ideas will become clear in a few minutes. In 1950, the oldest fixed date in human records was 1872 BC, the 7th year of King Sesostris of Egypt. This date has been verified by mentions of the texts in his 7th year of a solar eclipse. Now, it turns out we've understood gravity longer than any other force, and even by the 18th century, one could easily calculate the positions of all the planets, the moon, and the sun over time, such that one could predict with great accuracy when and where solar eclipses can occur. Thus, going back millions, although it doesn't do us any good, but for human records, hundreds of thousands of years, we can tell precisely when and where an eclipse occurred. And the eclipse mentioned in the texts from Sesostris' range turned out to be in 1872 BC. Counting backwards from there to the founding of the first Egyptian dynasty gives the date of the Egyptian dynasty's origin of 5,100 plus or minus 100 years before the present. Now, the reigning archaeological chronologies of that time had civilization emerging in the Middle East and in the Nile Valley and slowly diffusing out throughout Europe. In particular, the speculation was that the age of Stonehenge, the large stone monument in the southwest of England, was put at about 2000 BC, about 1,000 years after the building of the Egyptian pyramids, suggesting that over that time, the notion of building large stone monuments might have become something that could be embedded in a culture. In 1950, however, Willard Libby introduced his carbon-14 technique to date ancient monuments. And using a piece of wood found buried in the ground near the stones of Stonehenge, he got a date that was 1,000 years earlier, putting Stonehenge at the same date as the pyramids. The British archaeologist Stuart Piggott called this date, in typical upper-class British style, quote, archaeologically unacceptable, end quote, directly challenged the C14 dating technique, which had only been verified on objects that were known to be less than 1,000 years old. Using wood from ancient tree rings, it was shown in 1967 that indeed the carbon-14 ages are wrong because of fluctuating carbon-14 production in the atmosphere. But it turns out, ironically, they're wrong in the wrong direction for Professor Piggott's objection. Stonehenge is in fact hundreds of years older than the pyramids. Fluctuations in the carbon-14 production rate are caused both by the changing sun's magnetic field and its level of activity, which tends to expand out beyond the Earth and screen out, hold away from us, the cosmic rays coming in from the galaxy that actually produced this isotope, and also the changing Earth's magnetic field, which acts as a secondary shield against these cosmic rays, and, in addition, particles spewed out by the sun. Using tree rings, lake and ocean sediments, and corals, C14 ages have been calibrated back to 50,000 years before the present. That is, we've taken the apparent C14 age as measured by the C14 to C12 ratio and the simple calculation that C14 decays away at a constant rate with a half-life of 5,730 years, to the actual ages measured by other techniques. From tree rings alone, we have a record going back almost 12,000 years. The 10,900-year continuous record from Northern Europe shows corrections that range from minus 170 years, about 500 AD. That means you have to subtract from the age that you get from carbon-14 dating 170 years, to plus 850 years, 7,400 years BC. That is, you have to add 850 years to the age, almost a full millennium, which represents a 10% change in the carbon-14 composition of the atmosphere. There's big changes in this carbon-14 production rate. Now, we run out of tree rings about 12,000 years ago, but as I said, carbon-14 can be used to date things back to 50 or 60,000 years, and so we have to look to other proxies to calibrate this record. One thing we use is the sediments that accumulate in anoxic lakes and ocean regions, anoxic meaning lacking oxygen where no life exists. This is important because if there's oxygen in the lake or ocean sediments, there are also worms crawling around in the mud, and they churn up the mud and mix up the layers. But in anoxic regions where there's no life in these areas, as the sediment accumulates, it has retained its distinct individual annual layers called varves. And these can be incredibly useful in dating, analogous to the individual layers or rings of a tree. In Cariacao, off the Venezuelan coast, there's a beautiful record from foraminifera, little single-celled plankton in the ocean which form little calcified shells around them, and when they die, sink to the bottom of the ocean. In this place where the ocean remains undisturbed, you get individual layers, and there is an almost perfect match for German pine tree ring record over a 1,300-year period from 10,500 to 11,900 years before the present in these varves off the Venezuelan coast. That record goes back further to 15,000 years before the present, which shows that the carbon-14 age then is 2,500 years too young. It's way off by 2,500 years. And this pushes back the age at which the last ice age peaked. To go further into the past, we actually use coral reefs. Corals actually take up dissolved uranium from the seawater in a fixed ratio to the element calcium with which they build most of their shells. So the uranium to calcium ratio is well known. There's no fractionation factor, so we know the initial amount of uranium present. Uranium-238 decays through a rather complex multi-step process to ultimately produce thorium. Uranium-238 has a 4.47 billion year half-life. That's just about equal to the age of the Earth, so about half of it has decayed since the Earth was first formed, therefore there's plenty of it around. Uranium-238 decays by alpha decay to thorium-234, and then thorium-234, also radioactive with a much shorter half-life of only 24 days, decays into protactinium-234 via a beta decay, which, also being radioactive, decays in merely a minute to uranium-234, which through yet a further beta decay with a half-life of 244,000 years decays to thorium-230, which subsequently through alpha processes and beta processes and 9 more steps decays ultimately in 78,000 years to lead, the stable isotope. The uranium is water soluble, but the thorium is not. So all the thorium in the shells comes from the uranium-234 decay. This process eventually approaches what we call a secular equilibrium, in which the rate of uranium-234 decay and the rate of the thorium-230, which is produced from uranium-234, are equal. And any departure from this equality yields the age of the sample, this clock extending back to nearly 500,000 years. My colleagues at Columbia have sampled many corals from the Barbados and shown that there are corrections in the carbon-14 age that extend from 3,500 up to 3,500 years, about 20,000 years in the past, showing that the peak of the last ice age is not, as carbon-14 would suggest, 18 or 19,000 years, but is 21 to 24,000 years ago. What changes the C14 production rate? One thing is the weaker Earth's magnetic field. The Earth's magnetic field is generated in the core of the Earth by the swirling currents of molten iron and nickel that exist there at 5,000 degrees. These swirling currents of ionized gas, it's a plasma, of course, where the electrons are ripped off from the particles, from the nuclei, again, accelerating charges, making electric and magnetic fields, makes the magnetic field that we see today, north and south, aligning our compass needles. But by its very nature, this turbulent swirling motion is not steady or constant in time. It's constantly changing. And in fact, the direction, that is the location of the North Magnetic Pole, and the intensity of the field are both preserved in molten rocks, lava, and even human-produced ceramics as the material cools. Atoms themselves are little tops. Their electrons are circulating around and their protons are spinning. And again, these spinning charges make magnetic fields. The North Pole, if you will, of a magnet likes to align with the South Pole of the Earth's magnetic field. Opposite poles attract, and vice versa. And so as the magnetic field exists in the macroscopic world, the microscopic world of the atoms actually align with it. And the strength and direction of the field say how much and how thoroughly they align. From these measurements, there's good agreement that shows that the magnetic field declines and the C14 ratio therefore increases as this screen against cosmic rays gets weaker from 50,000 years ago to 40,000 years ago, then plateaus for about 20,000 years, that is, the Earth magnetic field remains constant, and then starts steeply declining over the last 15,000 years and is still declining today. As an aside, I would note that there are also human influences on carbon-14 abundance in the atmosphere that will need to be taken into account by future archaeologists. The biggest effect is nuclear testing in the 1950s and 60s, which swamped completely the natural production rate of carbon-14. This is not all bad, although future archaeologists will need to be aware of this, but today we use this excess carbon-14 put into the atmosphere between 1951 and 1963 as a way to see how much carbon dioxide, C14O2, is absorbed into the ocean. We're producing enormous amounts of that today by burning fossil fuels. That also changes the carbon-14 ratio in the atmosphere because fossil fuels made from plants that are hundreds of millions of years old have zero carbon-14 in them because all the carbon-14 is decayed away. So we're adding this dead carbon-14 to the atmosphere, and then the carbon-14 produced by nuclear weapons says how much of that is absorbed into the deep ocean, taken out of our atmosphere, and therefore won't affect our climate in the future. In addition to the use of rings and cores to correct carbon-14 dates, the isotope ratios in the wood of each ring of the tree can also provide a detailed history of past climate. In this case, we're not using the carbon-14 necessarily as a dating technique. We're using the carbon-13 to carbon-12 ratio in the rings to learn something about the climate, where the calendar itself is given by the rings. The ring width and the ring density, the wood density in a given ring, strongly correlates with summer temperatures over the last 120 years when they've been measured by regular thermometers. And this allows us to construct a continuous temperature record over the last several thousand years in Europe. Over this time, the mean temperatures have fluctuated by about plus or minus 0.6 of a degree, as shown in this diagram. You see that the scale on the left ranges from minus 1 degree centigrade, that's almost 2 degrees Fahrenheit, to plus 1 degree centigrade from the average value. Now, you might not think that 1 or 2 degrees temperature would make a big difference, but in fact, it makes an enormous difference for people living in marginal circumstances, and it can even make a rather big difference for agricultural production. Two of the main features on this diagram are a peak between about 600 AD and 1200 AD, called the medieval warm period, and a valley between about 1400 and 1800, which is called the Little Ice Age. Today, as we know, the temperatures are rising rapidly and are near the peak of the last 2,000 years. The Vikings set off to colonize Greenland at the peak of the medieval warm period. They took cows and sheep and large numbers of people, built 2 large cities on Greenland, and sustained themselves on the kind of agriculture they were used to in Norway from whence they came. However, as the temperature started to decline, the growing season shortened. The amount of grass that they could produce and therefore store for the winter, which was rather harsh in Greenland, meant that fewer and fewer of the animals survived the winter, and by about 1350, the entire society disappeared. Likewise, the Little Ice Age. You're all familiar with the great 17th century painters of Holland, and they always show Dutch people skating on the canals. Well, the canals in Holland very rarely freeze these days, but back in the Little Ice Age, they froze all the time because the temperature was sufficiently lower. Yes, it was only about 1 degree centigrade or a couple degrees Fahrenheit, but that's enough to make a significant change. These are the kinds of temperatures we can expect in the future as global warming comes along, changes that are maybe 5 times as large as this. Using isotope ratios from wood also allows us to determine the humidity and temperature records directly. The carbon-13 to carbon-12 ratio correlates with moisture levels, since, as I told you last time, the carbon is sucked into the leaf by little stomata on the bottom. These are little breathing holes, and when it's very dry, they close down so as to prevent water from leaking out of the tree. The tree wants to preserve the water. When it's very wet and there's plenty of water for the tree to absorb from the ground, these holes open up again because then more carbon can flow in, and as a consequence, the tree can grow more rapidly. As the holes narrow, the ability for carbon to get in is less, and therefore carbon-13 is less heavily discriminated against. It's hard to be picky when you can't find many molecules to join them together in your initial carbon chain. A 0.1% change in the ratio of carbon-13, carbon-12 corresponds to a 15% change in humidity. And so by dipping into a ring whose age we know precisely from simply counting in, we can determine the humidity in the year that that ring grew. Likewise, the ratio of oxygen-18 to oxygen-16 and deuterium, heavy hydrogen, to normal hydrogen are direct measures of temperature, since, as we've said several times, the rate at which the heavier molecules move is slower, and for them to evaporate from the ocean, the temperature has to be higher. So higher concentrations of the heavier isotopes correspond to higher temperatures. And again, dipping into a ring whose age we know precisely allows us to measure the temperature over that period of time. These ratios in the oldest trees have shown an abrupt end of the last ice age, starting about 10,900 years ago. Tree rings provide an unambiguous calendar, which greatly improves our confidence in our atomic methods of dating and provides a history of climate over the last 12 millennia. But as we shall see, the major climate cycles on Earth, which are driven by astronomical phenomena that oscillate over much longer timescales, need some other clock. To measure these, we need a record that extends back much further in time. And we have found such a record frozen in the glaciers of Greenland and Antarctica. More about that next time.